no way. There's no way that's the case. Oh, so it's -5.
Measurements in the realm of physics, or any other science for that matter, you always have to think about the tools that you're using. And in our case, we're using a photomultiplier tube. And you also have to think about what sort of a response or signal you generate or tool generates for the given stimulus. In our case, our stimulus is gamma rays that are coming off of positrons that got annihilated, and our signal is coming out of our PMT.
So the most difficult parts were probably the calculations back in the first semester. We had to learn a lot about antimatter, vacuum systems, and more. Modeling molecular flow is very challenging, and we got over this obstacle by using and refining our current skills in electricity and fluid dynamics that we previously established in our mechanical undergrad. Another challenge was keeping up with the material, as this was a field that is completely new to us, and we had to learn in such a short period of time to keep up with the deadlines. And another thing is that because it's such a complex subject, simplifying it in reports and presentations is something that was a little difficult to do.
Working in a large group that included students from the physics department, it was often the case that we would have conflicts in our schedules and were unable to find a time where we could all meet on campus. To overcome this obstacle, we made use of video conference calls, as well as splitting up our group into subgroups, and those subgroups working on specific parts of the project, rather than all of us working on one part at a time, to ensure that we were optimizing our time and working more efficiently.
Finding funding for this project was difficult. A lot of time was spent in creating proposals to be sent out to potential sponsors. But the one factor that really helped us along the way was the fact that we were one of the first undergraduate student teams to be conducting an antimatter trapping experiment at a undergraduate and university level. Normally, a project like this or antimatter trapping in itself is done at institutions like CERN.
For this project, I worked on the magnetic field system with the engineering and physics majors on our team. The purpose of the magnetic field is to guide the positrons from the radioactive source all the way to the annihilation zone. To ensure that all the magnetic field lines generated in the center carrying the positron beam and in the annihilation zone, a model was created. Creating the model was a bit challenging. It depended on the coils that were available, and finding coils that fit with the tubes of the system was a bit of a struggle, but we were finally able to finalize on the coils to be used and were able to model the magnetic field throughout the system.
The impact of this project is vast, not only for sponsors that sponsored this project, but also for York University, the Lassonde School of Engineering, and the physics department. Upon its success, the project could potentially open up a new wave of interest within the physics realm for students coming out of high school. On top of that, the ability to bring antimatter research to teaching labs and allowing York University students to conduct antimatter experimentation is really huge. This allows for greater accessibility of antimatter research, which then further paves the way into the improvement and development of the many use cases of antimatter in real life. Use cases such as positron emission tomography, aka PET scans, space hardware testing, and also atomic scale fracture identification.
For the last 6 months, myself and my colleagues in the Department of Physics, we were working together to find a suitable protective shield against high-energy positrons. We concluded that cave design, 4-inch thickness of lead material, would help us to reduce the exposure risk of these high-energy positrons. Moreover, we made sure that we are following the regulations, health, and safety of Ontario and York University.
In front of you is the assembly for the Antimatter Containment Unit. Let's take a look at how it works. A high-energy positron is emitted from a radioactive source and is headed towards the tungsten moderator. As the positron makes its way through the moderator's crystal structure, it loses some energy to the tungsten atoms, after which the positron is accelerated to a known speed set by the voltage applied on the moderator. After going through the moderator, the positron makes its way towards the first stage of the trapping process, guided by external magnetic fields. The positron then enters a region where nitrogen gas is present. This is the first stage of the two-stage trapping process. As the positron makes its way through the nitrogen region, it interacts with the gas and has the probability of losing some of its energy. Whenever the positron loses energy, it goes down to a lower energy step. After the positron leaves the nitrogen region, it enters the second stage of the trapping process. In this stage, the positron oscillates back and forth within this region as it does not have enough energy to escape to the previous stage. At this point, the positron stays trapped within the system until it is released. When the positron is prepared for annihilation, it is released and travels towards the annihilation zone. As the positron approaches the end of the vacuum system, it undergoes annihilation as soon as it comes into contact with a free electron. This annihilation produces two gamma rays in opposite directions, which are then detected by gamma ray sensitive instruments. In application, there will be more than one positron going through the system, and so these instruments will be used to collect information about the number of positrons trapped.